Hello everyone, myself Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the last session, we discussed about cutouts in wings and fuselage, and we've seen the functions of fuselage frames and wing ribs, and when the cutouts are there, so how a panel length and depth will be considered. So all that things we have considered in the last class. In the present session, we discussed about principles of stiffener or web construction. So now here the learning outcomes in this module are, at the end of this module, the students are able to analyze cutouts in fuselage and wing and solve problems in cutouts. Now since this may be the principles of stiffener and web construction, so here we are going to consider how a stiffener can be calculated, stiffener will be constructed, and how a web can be constructed. So what are the conditions that we have to follow, that all we will see in this, and probably we'll take an example of a problem so that you will well understand by considering the example problem and how stiffener loads and loads in the web can be calculated. So now the frames and the ribs are themselves they're fabricated from thin sheets of metal, and therefore they require the stiffening members to distribute the concentrated loads to the thin webs. If the load is applied in the plane of the web, the stiffeners must be aligned with the direction of the load. So this is very important point. And if at all a load is applied, so the load should be applied in the plane of the web of a stiffener, and it should be aligned with the direction of the load. So whenever you try to add a stiffener in a structure, so when the load is applied, so the load should be applied in such a way that it should be aligned with the direction of the load. So the stiffener should be placed in such that in the low direction only you have to add the stiffener. Alternatively, if that is not possible to add the stiffener in the direction of the load should be applied at the intersection of the two stiffeners. So that is another point what we are taking here. So if you are unable to add the stiffener in the direction of the load, then alternatively what you can do is you can add the load at the intersection of the two stiffeners, so that each stiffener resists the component of load in its direction. Okay, so to understand this, let's consider one example problem in which the basic principles of stiffener or web construction are illustrated. So you consider this diagram and let's see this question. A cantilever beam as shown in figure carries concentrated loads as shown in figure, and is asking to calculate the distribution of the stiffener loads and the shear flow distribution in the web panels, assuming that the latter are effective only in shear. Okay, so this is the question that is given, and is asking to calculate the stiffener loads as well as the shear flow distribution. So to understand this problem, first you need to understand the diagram that is given. So this is the cantilever beam which is given here, and in which you can see here there is 4 panels he has given. This is the first panel, and this is the second panel, and this is the third panel, and this is the fourth panel. Now if you look at this cantilever beam, there are only two loads that are applied. One load is applied at point F, that is vertically acting downwards, that is 5000 Newton, and another load is acting at K, that is 4000 Newton at an inclination of 60 degrees with respect to the vertical axis, that is HKD. Okay, so what the 2 points we have seen in the previous slide, whenever the loads are applied, the stringers are placed, they should be aligned in the direction of the load. Now that first point you can see here. So here the load is applied. How the load is applied? It is applied that the stiffener is placed in such a way that it is placed in the load applied direction. Okay, so the vertical stiffener is placed in such a way that it is placed in the load applied direction. The second point also we have seen, that is, if this is not possible to apply the load along in the stiffener direction, so what you can do is you can apply the load at the intersection of the stiffeners. So clearly in the diagram if you see, so this is the vertical stiffener, and this is the vertical stiffener what we have, and this is the horizontal stiffener what we have. So at the intersection the load of 4000 Newton is applied. So though it may be the inclined load, but it should be applied at the either in the direction of the load of the stiffener, or it must be applied at the intersection of the two stiffeners. So this particular diagram which is given to us, it is following both the conditions, and the first load is applied in the stiffener along with the aligned with the stiffener, and the second load is applied at the intersection of the two stiffeners. So that is, you have to understand. And he has given the lengths from K to D, that is 200, and K to H is 100 mm, and each panel 1, 2, 3, 4, that is, he has given 250 mm load, and these are the stiffeners. So all these are the vertical stiffeners, and these are the horizontal stiffener, whereas ABCD is nothing but the upper flange. ABCD is upper flange, whereas EFGS is the lower flange. So first we need to consider stiffener loads followed by the shear flow distribution. So to go with this problem, what you need to do is you need to consider the free body diagrams of each stiffener separately. So free body diagram of either vertical stiffener or horizontal stiffener, they have to take separately, and we need to draw the free body diagram and represent all the shear flows and the loads and the lengths on it. Okay, so if you try to look at into this one, and as we assume this as for first, and so here let's assume this as first panel. Okay, and in which you can consider this as panel 1, and let us assume the shear flow in this panel as Q1, and let us consider this as panel 2, in which the shear flow is assumed as Q2, and this is the panel 3, and in which the shear flow is assumed as Q3, and this is the panel 4, in which the shear flow is assumed as panel Q4. Okay, so let's try to consider any of the first to understand this analysis. First, let's try to consider the vertical stiffener HKD, and the horizontal stiffener JK. So JK is the horizontal stiffener, and HKD is the vertical stiffener. So let's try to consider these horizontal stiffener HKD, horizontal stiffener JK and vertical stiffener HKD, and let's try to draw the free body diagram for it, and let's try to represent all the forces and respective distances as well as the shear flow. And while, for example, let's try to see one example here. If I am trying to draw HKD, vertical stiffener HKD, okay, and in which we have here, this is point D, and this is point H, and this is point K, okay, and through which load of 4000 Newton that is acting, and which is at an angle of, it is 60 degrees, okay. And so therefore, first thing what we need to consider here you need to consider the since this is a vertical stiffener, so the load what you get here is 4000 cos 60, which is acting downwards. So when you take 4000 cos 60, that is acting downwards, and you can remove this, okay, because the vertical component of 4000 Newton acts in the line of action of the HKD stiffener, that is a vertical stiffener, and followed by its horizontal component now becomes what? 4000 sin 60. Okay, but anyway, we nothing to do with this horizontal component because we are considering only the vertical equilibrium, that is vertical component. Now let's try to look in this direction. Lengths are given here. So from here to here the length is 200 mm, and whereas the length from here to here is 100 mm. And next what we need to represent, so load representation is over, the free body diagram, length we have represented, the only thing is left is shear flow. Now how to represent shear flow? So the shear flow in this panel is taken in the downward direction, whereas when you represent here, you have to represent in the upward direction, equal and opposite. So from here the shear flow, here it is Q1, okay. Similarly the Q2 shear flow in panel 2 is represented in the downward direction. When you draw the free body diagram, it should be represented in the upward direction, equal and opposite. So again Q2 position is like this one, okay. So this is the vertical equilibrium for the HKD. Similarly, when you try to look for JK, so this is J and this is K, and at K we know that a component of 4000 Newton acts here, okay. So component, that is a horizontal component, and first let's try to represent that. and the horizontal component of that becomes 4000 into sine 60 is the component, and then the length is 250 mm, and let's try to represent the length of that. It is 250 mm. Now we need to represent the shear flow. So JK is the horizontal stiffener here, and if you look at the above portion, Q1 is the shear flow, that is the panel 1 which is taken in the right direction. So therefore in the free body diagram you have to represent the equal and opposite shear flow to the left side. So here we are representing Q1 here. Similarly, on the below, that is below JK, there is a Q2 shear flow which is acting in the left direction, and therefore in the free body diagram you have to represent that Q2 in the right direction, Q2. So this is how the free body diagram. If you clearly draw this diagram like this for the vertical stiffeners and the horizontal stiffeners, almost the problem is over. Now after that, what we are going to do is we are going to apply the equilibrium equations. Okay, equilibrium. So now for this case we are going to consider the vertical equilibrium, and for this case we are going to consider the horizontal equilibrium. Okay, when you do that, you are going to get the shear flows straight away. So for JK, if you try to consider, sigma, if you try to write equation, what you can write, if you consider the positive direction to the right side, and you can write this as Q2 minus Q1 is the shear flow multiplying with the same length, that is 250, and plus 4000 sine 60 equal to 0. Okay, so this is the equation what you write, and again you can rewrite this equation in terms of Q2 and Q1, and then you will get an equation in terms of Q2 and Q1. Similarly, if you try to write the equation for this, what you can write the equation here, Q1 into multiply with its length, that is 200, plus Q2, both are acting in the upward direction, so I am taking positive sign, so Q2 into 100, and that must be minus 4000 cos 60 is acting downwards, so I am writing 4000 cos 60, that is equal to 0. Again, this is second equation. So what you can do here, it is you can consider first equation, that is in terms of Q1 Q2, second equation also is in terms of Q1 Q2. You can solve for both of them, and so that you will get Q1 and Q2. So by considering the horizontal and vertical equilibrium of JKD, HKD as well as JK, you are going to solve two shear flows, that is Q1 and Q2. So after the Q1 is Q2 is over, then you left with only the other two shear flows 3 and 4. Okay, so this is how the free body diagrams are considered for JK as well as HKD, which we have seen, and in which we got the equations in terms of Q1 and Q2, and therefore you can calculate the shear flows. Q1 as 11.3 Newton per mm, and you can calculate the shear flow Q2 minus 2.6 Newton per mm. Now let's move on to the next panel. So 1-2 panel is over. Now next move on to the next third panel. Now what you are doing here, it is we are considering the third panel like this. Okay, so in the diagram again we represent here you may have Q1 in the upward direction and Q2 in the upward direction. So here in the free body diagram, this is a free body diagram. So in the free body diagram you have to represent Q1 and Q2 in the downward direction and Q3 in the upward direction. So this you have to look for the main figure, and then you need to draw, and 2200 mm is the length and 200 mm is the length. So this is what we got it. So when you try to use this one, when you try to write this problem, so there are two ways for this, and if you look at the main diagram, there are two ways in finding this. Okay, so what are the two ways? So when you try to write for this one, when you try to draw for the C, J and G, and here the shear flow is Q2 is acting in upward direction, so you have to write Q2 here, and here the Q1 is again Q1, and here the Q2 is also acting upward direction, so you have to write Q2, and the left side is acting in the downward direction, so you can represent Q3 in the upward direction. Okay, so if you look at this one, and the vertical, this is a vertical stiffener what we considered here, and what you can write in terms of equation. So you can write this total depth is nothing but 200 plus 100. This is 200 and this is 100. So what you can write this equation, 300 into Q3, 300 into Q3, and that is equal to minus 200 into Q1 minus 200 into Q2 you can write. Okay, and since this is the vertical stiffener, and what you can add for it is nothing but you can even add 300 Q3, that is equals to 300 Q3, that is equals to 200 Q1 plus 100 Q2. So you know already the values of Q1 and Q2. You can substitute here and you can get what is the shear flow for Q3. So what we got, Q1, Q2. So Q1 we got is 11.3 Newton per mm, and Q2 we got minus 2.6 Newton per mm. And you can substitute here in this equation, you can get the value of Q3. That is our one procedure what we got. Or this 200 Q1, this 200 plus 100 Q2 from equation 1. 200 Q1 plus 200 Q2, where we written here this one. So 200 Q1 plus 200 100 Q2, that is equals to what you can write, 4000 cos 60. So either you can use like that, or you can substitute this is equals to 4000 cos 60, and straight away we can calculate without substituting Q1 and Q2 values here. So Q3 will be equals to 4000 cos 60 divided by 300, then you will get Q3 value. Either both are same. So either you can substitute Q1, Q2 values and you can get Q3, or you can write 200 Q1 plus 100 Q2 equation, that is equals to 4000 cos 60 from the vertical equilibrium of HKD. You can substitute and you can get Q3. So this is how the Q3 will be calculated. Okay. And now if you look at it for the fourth shear flow. So fourth shear flow, if you try to look for the fourth shear flow, let's try to go for the diagram. It's better to go through the diagram and understand fourth shear flow. So when you try to draw the equilibrium equation for the vertical stiffener, that is BF, and the shear flow Q3 is acting in upward direction, so we'll draw the shear flow, that is Q3 in the downward direction, and here Q4 shear flow is acting in the downward direction, so we draw Q4 shear flow upward direction. If you try to consider the vertical equilibrium for this, what you are going to get? So you are going to get the vertical equilibrium as the total depth is 300 mm. So 300 Q4 multiply its length 300 minus 300 into Q3. Okay, this is also 300 length for Q3, and then you have to add this also. So minus 5000 Newton, that is equal to 0. So 300 Q4, that you will get it as 300 Q3 plus 5000. Okay, so Q3 we already got from the previous cases, that is from the previous analysis, and here we got Q3 as 6.7 Newton per mm. So that you can substitute over here. You can substitute in this equation for Q3 is 6.7, and you can get easily what is Q4. So this is how the shear flows in all the panels will be calculated. So once the shear flows are done, then our important thing here we need to calculate is nothing but the forces in the flanges. Okay, so that also we will see how we will calculate the forces in the flanges. So first let's consider the first flange, that is ABCD, and in this flange let us consider PA as the load in the axial flange, such that we can write the equation as. So if you try to write the, look at the diagram, it's better to go to the diagram and see. Yeah, so here all the shear flows are there. So let's try to write this equilibrium diagram. So this is Q1 shear flow, and this is Q3 shear flow, and this is Q4 shear flow. We are drawing equal and opposite. Okay, such that what is the equation you can write here? You can write the equation as all the lengths are same, 250, 250, 250. So that you can take common, that is Q1 into 250 plus Q3 into 250 plus Q4 into 250. And let us assume the load in the flange is PA, so that you can write the horizontal equilibrium for the flange ABCD, and you can write this as PA, that is equals to 250 Q1 plus 250 Q3 plus 250 Q4. So we already know what are the values of the shear flows Q1, Q3, Q4. You can substitute here and you can get the force in the flange ABCD. Okay, and you can substitute values and you'll get 10,325 Newton, and it is a tensile force. Similarly, you can calculate the force in the lower flange, and when you try to write this equation, you will get PE equals to minus 250 Q2 minus 250 Q3 minus 250 Q4. Okay, so and then you can substitute the values of the shear flows Q2, Q3, Q4, and you can get the force in the flange, lower flange, that is equals to minus 6850 Newton. So the complete load distribution is shown like this one. Okay, so the complete load distribution is shown here, and 10,325 Newton is the force in the upper flange, and whereas 6,850 Newton is the force in the lower flange, and its respective shear flows. On the upper flange, the shear flows are given. So this is Q1, this is Q3, this is Q1, this is Q3, and this is Q4. Whereas this is Q2, this is Q3, and this is Q4. Okay, so these are the shear flows, and at respective points also, at C, at B, you can represent on the upper surface, and at G and at F, you can write the values of the shear flows what we got, and you can probably draw this complete diagram of shear flow. Okay, so that is how we solve the problems of principles of stiffeners and web construction. So you have to follow the principles of stiffener and web construction when the loads are applied, and when the stringers are taken, either horizontal stiffeners or vertical stiffeners are taken, they must be aligned to the either the direction of the load, or they must be placed at the intersection of the stiffeners. And then the calculations of the loads, shear flows as well as the loads will be considered by considering horizontal and vertical equilibrium of respective stiffeners. Okay, so thank you everyone for watching. So that's all from aerospace structure syllabus. So we've completed all the 5 units of syllabus. So thank you everyone for watching.